3 in the Keller Seismic series. My name is Brad Keeler. I'm the director of the Geo-Institute, and thank you for joining us this afternoon for another one of our amazing live stream events. We bring them to you every so often. We prefer more frequently than less frequently. And so we are here today. Armin Stuedlein from Oregon State University is going to be our featured lecturer in just a moment. Right now, I will tell you a few very important things that you may or may not know. If you don't know anything about the Geo-Institute, after you watch this presentation today, you should head over to geo-institute.org. And while you are there, you will learn about all things GI, including that we are a technical society with about 12,000 members, most of whom are geotechnical engineers and or geologists, and that we are part of the American Society of Civil Engineers. Of course, if you are enjoying what you see today, I think you will. You should click like, subscribe, get notifications, and we will let you know every time we post something to our YouTube channel. The last thing today is you will notice, or maybe you do not notice, I'm wearing my Geo-Congress 2020 Geo shirt winning design from our student competition. If you love our student members, and really who does not, I question a lot about you if you do not love our student members. You should go over to geoinstitute.org and contribute your $96 to join the 96 Club and donate to our student programs. You can choose either a Carl Terzaghi bobblehead for your time and effort, or a pair of beautiful Geo-Institute Shield socks. I would say suitable for framing, except I would rather have you wear those. With all of that out of the way, we now have a great presentation. Thanks again for all our viewers for joining us. And here to introduce the series and today's episode from Keller on the other side of America is Tim Avery.
Well, thank you, Brad. Good afternoon, everybody. Today, I'm very pleased to announce our third speaker, Armin Stuedlein. Armin is a licensed professional engineer and professor of geotechnical engineering in the School of Civil and Construction Engineering at Oregon State University. Armin received his MS in geotechnical engineering from Syracuse University in 2003 and his Ph.D. at the University of Washington in 2008. And he did that while he was working with several geotechnical consultant firms in Seattle. He is the vice chair of the Soil Improvement Committee of ASCE's Geo-Institute, editor at the ASCE Journal of Geotechnical and Geo-Environmental Engineering, and editorial board member for several other journals. Armin has received several awards, including the recent 2023 James R. Cross Medal for work done with former students and colleagues. With that, I give you Armin Stuedlein on liquefaction susceptibility and cyclic resistance of transitional silts with application to subduction zone earthquakes. Armin, please.
Yeah, good afternoon, Tim. Thanks so much for the nice introduction and allow me to share this work with you and everybody viewing in the audience. So I'd like to start out by acknowledging the sponsors for this work, without which we couldn't have been able to do what we've done. And as important are the sponsors are the wonderful colleagues and students that contributed to the work shown in today's presentation. Before I get too far, I just want to make sure that, Tim, you can see my screen.
Yes, I can.
Perfect. Very good. So with that, why don't we start the talk? I'm just putting up this screen here so that folks can come back later on to the video and see what are some of the works that underpin today's topic. But the bolded talks are the bolded papers are those from which I'll be pulling the majority of today's talk from. So we'll start with an overview of the basis for our findings, which rests within a database of cyclic laboratory tests. So we'll discuss the typical ranges of soil properties and parameters that comprise this database. Then I'm going to start with an overview of resistance, first addressing hysteretic behavior, linking that to a means to identify liquefaction susceptibility. I'll introduce some metrics for quantifying liquefaction and hopefully improve assessments of whether we might have clay-like or sand-like behavior, and a brief discussion of why ultimate hysteretic behavior might matter if you're in a subduction zone like in the Pacific Northwest. With that, I'm going to switch gears and talk a little bit about loading, specifically with regard to the number of equivalent cycles that we might expect for subduction zone earthquakes as a result of some preliminary analyses that we've done. And then I'm going to circle back to resistance and discuss the means with which to estimate the cyclic strength of these silt soils for use with the simplified method. But we need to talk a little bit about our experimental methods, and our work really does start in the field. For those of you who have experience or wish to gain experience with silts, which really might transition from non-plastic materials to high plasticity materials, getting intact samples can be a challenge, but we've identified a series of best practices that really work for us. It starts with getting stainless steel tubes. These won't rust in the moist room. They'll reduce friction upon extrusion of your samples. Then we apply a 5-degree cutting edge to the tips of our Shelby tube samples, basically following the prescriptive approach by Dharma Widjewikreem at UBC. So we're not reinventing the wheel there. That's really good practice. Naturally, you need to use mud rotary drilling and use appropriate sampling strategies like the Osterberg piston sampler. At that point, our samples need to be sealed very well, padded, and transported to the laboratory without aiming for those potholes on the way back. From that point on, we store our samples carefully in a climate-controlled environment. We cut our tubes in half or thirds in order to minimize the extrusion length of samples, and we always push in the direction of sampling to prevent stress reversal. And with these tactics, we can get very good specimens for cyclic testing. So the materials I'll talk about today will all comprise intact samples. There'll be no results or analyses based on reconstituted samples. And that's critical because these materials exhibit a natural soil fabric, which is directly responsible for their cyclic resistance. These materials are encountered in the Pacific Northwest, where we operate in relatively shallow depths, at least for our study sites, but they can extend to depths of up to 60 meters in some locations, particularly in deltaic and estuarine offshore or near-shore coastal environments here in Oregon and Washington. If we take a look at our typical compression curves for some of our materials, I've just got a sampling here. You can see a distinct effect of plasticity, where higher plasticity samples or specimens will exhibit high compressibility, and low plasticity samples will exhibit a more rounded compression curve. I should point out that our materials are naturally over-consolidated, typically about 1.5 to 4. In fact, 1.5 to 3 is most typical, indicating that there has been some aging of these specimens since their deposition. However, we have taken our natural intact specimens to normally consolidated conditions in order to bound the cyclic resistance that we might expect for those conditions. Drawing from our database, you can kind of get a sense of the statistical distribution of plasticity index, vertical effective stresses in the field, which is the consolidation stress we applied in the laboratory, as well as the OCR. In general, our median plasticity index for our samples is about 11. And we can see that non-plastic specimens might range from 8 to 13%, depending on the cyclic shear strain amplitude to which we've loaded the material. On the upper end, at about PI greater than 30 or so, we also have relatively poor representation, which decreases as the amount of shear strain indicated by the symbol gamma on the middle of your screen is shown. Likewise, the median effective stress and range in stresses are relatively narrow and are centered at around 125 kilopascals. So we're not really going to encounter significant effects of stress dilatancy or the K sigma effect, but we're working on that as we speak. Likewise, the typical median OCR is about 2.0, and 90% of our specimens have a over-consolidation ratio less than 3. The key here is that the distribution of these parameters do vary as a function of strain level, and that's going to potentially impact some of the models we've developed. And so we should need to be aware of limitations if we do go ahead and use any of these models. So with that in mind, I'd like to step into the first part of cyclic resistance. And we'll do that by comparing a couple of specimens and typical properties and then cyclic responses associated with these specimens. So in the top portion of the graphs, letters A through D, we've got specimen B14-8. This is a low PI material with a PI of 13. OCR of 1.5, and a vertical effective consolidation stress of about 160 kilopascals. The specimen shown on the bottom is a non-plastic specimen with a higher OCR, but the same vertical effective stress, or at least similar. And you can see that the cyclic stress ratio, defined as the cyclic shear stress amplitude divided by the vertical effective consolidation stress, is relatively similar between these two specimens. That being said, there are some notable differences. Number one, the specimen on the top, B14-8, has a higher cyclic resistance, and that's due to its plasticity, which outweighs the effect of the lower density and higher OCR for the non-plastic specimen. And we can see that the initial rate of pore pressure generation at a shear strain of 3% is quite a bit lower for that plastic specimen relative to the non-plastic specimen. That being said, despite their differences in cyclic resistances, both of the specimens here exhibit cyclic mobility, indicated by transient loss of shear stiffness and pore pressures exceeding 95%. And so we like to call this kind of behavior sand-like in regards to their pore pressure generation characteristics and their loss of shear stiffness. Now let's compare low plasticity and higher plasticity specimens, and we're trying to constrain some of the variables in the same manner. So the specimen in the top has a relatively high plasticity index with 26, but it has a similar OCR compared to the low plasticity specimen, which has a PI of 15. Again, the vertical effective stresses that these specimens have been consolidated to are similar, and they're subjected to similar CSRs. In this particular case, they share a near identical cyclic resistance. Now, in this case, again, we've got a similar OCR between the specimen, but the density of the lower plasticity specimen is quite a bit lower, but its effect of increased density in terms of cyclic resistance is offset by the reduced plasticity. So as we increase in plasticity, we expect greater cyclic resistance in general, but here it turns out to be a canceling of effects for these two particular specimens. The plasticity specimen does have a higher rate of initial pore pressure generation at 3% strain and slightly higher pore pressure at the very large shear strains, representing its ultimate behavior. But regardless, for these two specimens, they both exhibit what we like to call clay-like behavior, because the first cycle of loading, which includes exceedance of 3% shear strain, is relatively ovaline, and that shape of the hysteretic curve is maintained. So we don't see a transient loss of stiffness or pore pressures approaching 100% in these cases. In the comparisons that I've done here, we're identifying terms like sand-like or clay-like, and that begs the question revolving around how we might identify liquefaction susceptibility. And so I'd like to take this opportunity to point out that a workshop report summarizing the discussions on liquefaction susceptibility that was held at the OSU campus this past September is now available for download. And I've got the link down there in the bottom right-hand corner. We had wonderful participants hailing from a variety of countries and from a variety of different academic or government agency institutions, and we included practitioners. So I really recommend taking a moment to read through the report, the summary of the discussions, and particularly the extended abstracts submitted by the participants that can be found in the appendix of this report. But I did want to talk a little bit about a couple of key items that were discussed. One of the key items revolved around how we might identify liquefaction susceptibility. Should material behavior or inherent characteristics be the sole consideration, for example, plasticity, or mineralogy as another example, or should liquefaction susceptibility consider both elements of material characteristics and state? And so by state, we're thinking relative density and effective confining pressure, or void ratio is probably a bit more appropriate for these silty materials. And so discussions describing the pros and cons and different perspectives on this item number 1 are described well in the report. Another key item that was discussed was terminology and the usage of available liquefaction susceptibility criteria. In general, when we think about liquefaction susceptibility, I prefer that the focus be on the behavior of the material. And that can be quite different when the purpose of an assessment is to select the cyclic strength of a particular material. And so just to expand a little bit more on that, there are 2 widely available criteria that are available. One is based on specimens retrieved from Turkey following the 1999 Izmit earthquake, and these materials exhibited cyclic mobility type behaviors associated with liquefaction, and again, were retrieved from sites that exhibited ground failure for these silty materials. And so the idea there is that liquefaction susceptibility is based on hysteretic behavior. Another widely available and used susceptibility criteria is the Boulanger and Idris approaches, where liquefaction was defined carefully and narrowly as being applicable to those soils for which penetration resistance-based triggering models could be used to quantify the cyclic strength. Hence, maybe a more appropriate term is the cyclic strength evaluation criteria. So it's important to note that these models, if that use that term for these criteria, they do differ in their intent and purpose, and the workshop report do discuss similarities between these approaches and their differences. But it is quite worthwhile to point out, and this was actively discussed during the workshop, that transitional soils will span a range in behavior. We've seen soils with PI19 that exhibit liquefaction tendencies, and also soils with PI10 that do not. These kinds of soils can be reliably sampled, and as a result, they should be sampled in order to quantify susceptibility, their cyclic strength, and what the potential is for strain and the corresponding lateral displacements. Likewise, both authors emphasize that just because a material might not liquefy, that doesn't mean we need to turn our back and not pay attention to the potential for cyclic softening. And so, these kinds of elements are described well in the report, and I do point you to it. But the end goal here is to point out that differing models may have different intents and purposes, and we need to pay attention to the nuance between available criteria. So with that in mind, and thinking about what value there might be in identifying liquefaction susceptibility, I just want to clearly state herein, in this work, we define liquefaction as transient loss of all or nearly all shear stiffness, and that high positive excess pore pressures are generated in an ultimate condition. We also look for hysteretic behaviors that are associated with cyclic mobility. This means alternating contractive and dilative tendencies, where we may have periods of dilation hardening throughout any given cycle of loading. This could be important in terms of how we look at liquefaction susceptibility, because we can identify the potential for critical failure mechanisms, which might not be associated with evidence of liquefaction at the ground surface in terms of sand boils specifically. And I point to the case of this particular bridge from the Gear 2010 report, and then expanded in analysis and detail by Ben Turner and colleagues at UCLA, where liquefaction at the toes of a deep foundation caused settlements. And so a site where there was no sand boils, but evidence of deep liquefaction that we might not necessarily think about considering aspects of susceptibility. So with this in mind, we can quantify certain hysteretic metrics to obtain objective assessments of behavior. We might think about quantifying the angle of the shear stress, shear strain hysteresis prior to and following unloading, as shown by angle theta in the upper right-hand corner. Up here, we might think about the cyclic shear stress difference at the origin, or at shear strain, where the shear strain is equal to 0, where the degree of reduction over various cycles can be an indicator of progressive loss of strength. We might think about the transient shear modulus within a given cycle, or the tangent minimum shear modulus. And we can also, as you might expect, consider the maximum excess pore pressure that's generated. Now, these two items here, the cyclic shear stress difference and the minimum tangent shear modulus, these elements can be biased based on the shear stress amplitude. And so we like to normalize these two metrics by the maximum shear stress amplitude. And in the work herein, we'll largely focus on pore pressure generation and the minimum tangent shear modulus. But with this in mind, we can assess differences in behavior at typical cyclic failure criterion, such as 3% single amplitude shear strain in the cyclic direct simple shear test, and then how that behavior might evolve at larger cycles associated with shear strains that have exceeded 5% shear strain. So let's take a look at one example of a non-plastic material that at 3% shear strain exhibited what we might call intermediate behavior with a pore pressure generation of 93% and a minimum tangent shear modulus that's 10 times the shear stress amplitude. So at this level of, or this selected cyclic failure criterion, we don't see what we would call liquefaction tendencies. However, if we continue to cycle this particular specimen to approach perhaps 10% strain, we can see that the excess pore pressures approaches 100% and the minimum tangent shear modulus goes to 0 in a transient basis. So its behavior transitions to what I would like to call sand-like. If we look at another specimen with a plastic index of 27, we can see that at 3% shear strain obtained in the first cycle, we have a generally ovaline hysteretic loop in terms of its shape, and that shape is maintained throughout fairly significant amplitudes of shear strain. And so we would call its ultimate hysteretic behavior clay-like. And then we have the case of a low PI material with a PI of about 11. At the 3% cyclic shear strain failure criterion, we're only experiencing or observing about 80% excess pore pressure. Our shear modulus in terms of the minimum tangent is about 12 times the cyclic shear stress amplitude. And we might call that behavior in the red hysteresis loop to be associated with clay-like behavior. But as cycling goes on, and we accumulate increments of shear strain with each cycle, we can see that we lose our shear stiffness and the material exhibits 100% excess pore pressure to ultimately demonstrate sand-like behavior. So the question then centers on how can we relate the laboratory behavior to the field response. In part, to answer this question, we should point out that this last specimen that we discussed was derived from an investigation we conducted at the Port of Longview, which we call the OSU blast array. And at this particular site, we instrumented the subsurface, including this low plasticity soil deposit with a variety of instruments that allows us to compute stresses, strains, and link them to the excess pore pressure that was generated under a variety of techniques. One of the techniques was through collaboration with the NERI at U Texas NSF-funded center headed by Ken Stokey and Brady Cox. And we applied T-Rex over our instruments and were able to generate excess pore pressures associated with a maximum shear strain of about 0.15%. The next day after our pore pressures dissipated, we loaded up some blast casings with explosives and conducted a controlled blasting experiment in which you see the generation of excess pore pressures associated with the 30-second blast program to achieve strains in excess of 1%. And this work, overarching goal was to link laboratory and field responses. So what I'm showing here is the variation of DSS equivalent shear strain measured in the field or converted from measurements in the field to the residual excess pore pressure. I'd like you to focus on the blue and black markers representing two of our instrumented elements. And what we can see is that the maximum shear strain amplitude increases, the excess pore pressures begin to rise. And in terms of residual excess pore pressures, we basically exceeded just over 60% excess pore pressure at that maximum shear strain amplitude. Again, this material is a low plasticity deposit with PI ranging from 11 to 19. And if we compare the blue and black circular markers to the orange triangles, which represents a silty sand deposit during the Superstition Hills earthquake at the wildlife site, we can see that the excess pore pressure generation looks an awful lot alike to one another. And so comparing again our large strain sand-like cyclic behavior in a stress-controlled direct simple shear test, ultimately this material in the laboratory demonstrated liquefiable tendencies in sand-like behavior. And that appears to be linked to the smaller strain liquefaction tendency in the field under dynamic loading. And so it sure seems to me like these transitional low plasticity silts could liquefy if loaded dynamically to sufficient duration and intensities. But indeed, this liquefaction may occur at smaller strains than what might be implied by stress control testing. But regardless, it appears that the ultimate hysteretic behavior in our stress-controlled cyclic tests is necessary to reveal the potential for liquefaction. So that brings us back to how we might use the hysteretic metrics for liquefaction to identify the potential for liquefaction susceptibility. And so we can compare behaviors in terms of our hysteretic metrics at those loading cycles corresponding to a cyclic shear strain failure criterion of 3% relative to the last cycle of loading associated with shear strains that were larger than 5%. And at 3% shear strain, many of our specimens would be qualified as clay-like or generally intermediate. But as the number of cycles increased and accumulated, many of these samples or specimens transitioned to demonstrating sand-like behavior. So we can track the red triangle where a specimen was at an intermediate state and then transitions to the red triangle at the ultimate behavior. Likewise, we can see a specimen that was originally clay-like at 3% shear strain transitioning to sand-like at very large shear strains. So we can use our hysteretic metrics in terms of minimum tangent shear modulus and maximum excess pore pressure ratio to identify or propose a possible set of criteria to objectively, although we set these thresholds in a subjective manner, but at least we can quantify the metrics objectively in terms of the pore pressure generation potential and shear minimum tangent shear modulus at large strains. And so these guidelines may serve as a means to identify ultimate hysteretic behavior and potential for liquefaction susceptibility. Now, you might be wondering, what if you don't have cyclic test data? And that's going to happen more often than not. Well, it turns out that we can map our hysteretic metrics and our general categorization to the Bray-Sancio liquefaction susceptibility criteria, which did focus on hysteretic behavior. And we conclude that those criteria do seem to generally capture what we've observed with our specimens. You can note that we have very few specimens, just 2, that have a water content to liquid limit ratio less than 0.85. So it doesn't seem like this metric is relatable for the silts in our database, but it also begs or links to this concept of inherent susceptibility or a materials-based susceptibility, which is a perspective that gained traction for some of the workshop attendees at the peer workshop in September. And so there could be a basis for potentially dropping state-based considerations, at least based on the data that we have for identifying liquefaction susceptibility. Well, what about the cone penetration test? Very popular tool for all the right reasons here in the Pacific Northwest. And we often use it as a screening tool for liquefaction susceptibility through the soil behavior type index. So for each of our boreholes, we conducted, from which we retrieved our samples, we conducted cone penetration tests in fairly close proximity to the borehole. And for each sample interval in terms of depth, we took the geometric average of the adjacent cone penetration test based I sub C so that we can make comparisons. And in the graphs to the right, I've got open markers, which represent distinguished hysteretic behaviors for a cyclic shear strain criterion of 3%. And in the filled markers, I've got the hysteretic metrics shown in the graphs for the last cycle of loading, representing ultimate hysteretic behavior. And at 3% shear strain, you can see very little correlation between our hysteretic metrics and the soil behavior type index. As we go to the ultimate behavior, we're seeing that we have soils that exhibit I sub C almost pushing up against 3.0, so beyond the clay, the silt mixtures to clay soil type transition of 2.95, which exhibit 100% excess pore pressure generation and a minimum tangent shear modulus of 0. From our standpoint, for the materials that we've encountered, it does seem like there are some issues with the soil behavior type index for use with liquefaction susceptibility judgments. And that was another key topic discussed at the workshop, in which the I sub C thresholds that may be commonly used really hail from a distribution of possible soil behavior type indices that represent transitions from sand-like to clay-like behavior. So in this discussion, we've talked about ultimate hysteretic behavior, and that seems to be aligned with this inherent or material susceptibility concept. The question is ultimate behavior appropriate for these silts when dealing with short crustal earthquakes? Perhaps not, okay? But up here in the Pacific Northwest with the long duration megathrust earthquakes, it sure seems like we'll be encountering a large number of cycles of high intensity in which ultimate behavior may be revealed under the earthquake ground motions. So we really need to understand what the expectations are for us in the Pacific Northwest. And that begs the question, just how many cycles of loading are we talking about? So the key to this rests with a model that we tend to relate the relationship between cyclic resistance ratio and the number of cycles of loading. And in order to understand more about the loading, we're going to start by assessing this exponent B, which controls the curvature of the CRR end curve. And so that brings me to the second thrust of this talk regarding the loading. And the material presented here is available in a separate peer report that was released earlier this year. So we start with looking at our soils in our database, and we've assembled 20 suites of cyclic tests in which we could obtain a reliable curvature exponent B. We looked at a variety of soil variables, and we would have liked to use the void ratio and plasticity index and OCR, but the plasticity index and the void ratio are correlated, as you could expect. It's much easier to get the Atterberg limits from a split spoon sample, so we elected to use the plasticity index. On the other hand, it turned out that the overconsolidation ratio was statistically insignificant in terms of predicting exponent B. So by assessing the data in our database, we're able to develop a simple linear regression model that relates the plasticity index to the curvature of the CRR end curve through exponent B. Naturally, there's a bit of scatter, and we hope to improve the resolution of this model as we continue to do our work. In the meantime, this gives us a sense of how the curvature of the CRR end curve might vary with PI. But what does that, or how does that help us understand the number of equivalent cycles associated with the earthquake ground motion? Well, it's been shown by several researchers that the curvature of exponent B controls the number of equivalent cycles for a given ground motion. So we've elected to use a publicly available subset of the next generation attenuation subduction database, which included 500 two-component motions. And then we screened those motions on the basis of site class. So we only admitted observations from site classes C, D, and E, which are those in the Pacific Northwest where we find our transitional silts. We didn't screen out any motions on the basis of PGA, magnitude, or distance. We wanted to allow or admit as many motions into our assessment as we could. So in the graphs here to the right, we'll stop at the top, or start at the top rather. We can see the variation of the number of equivalent cycles with earthquake magnitude within this subset of the NGA database. And what we can see for a B of 0.06, again here at the top, there's essentially no correlation between moment magnitude and the number of equivalent cycles. If we look at the middle graph, we've got a B of 0.14. This is now going to be appropriate for slightly plastic to non-plastic silts. And we see that the sensitivity to moment magnitude picks up. And as we look at the bottom right graph with a B of 0.34, this has been suggested to represent dense sand by work from UC Davis. We can see that we've got the greatest sensitivity to moment magnitude. That being said, the scatter is really quite large, and that's because we're not considering things like distance, intensity, or other potential controlling factors on the number of equivalent cycles. But I just want to point out, for plastic silts, maybe with a PI of 30, we're talking about 1,000 cycles of loading. But there's no significant variation there because the curvature of the CRN curve is essentially flat. So we've pointed out the variability, we've pointed out the cycles and how large they can be relative to what we've expected from crustal motions. And with regard to the variability, it looks like for simple models that only consider moment magnitude, the use of the mean alone in these trends is rather questionable. So here I've got the geometric mean number of equivalent cycles shown as a strong black line amongst the various ground motions for a couple of different bins of moment magnitude. So up at the top, I've got earthquakes from subduction zones with magnitude ranging from 6 to 7. And down here, I've got the Tohoku ground motion set. And around that solid black line, I've got every other motion indicating the uncertainty in number of equivalent cycles and its variation with exponent B. I suppose the geometric mean shown here could be used as a starting point for the planning of your cyclic test programs. But in general, in order to relate to previously reported equivalent cycles at magnitude 7.5, largely representing crustal zone motions, our motions are in subduction zones do provide a larger number of cycles. So I've got relationships here in our peer report that prescribe the geometric average number of cycles for a given bin of moment magnitude earthquake. And down here in the bottom right, we're comparing to those developed from largely crustal motions, although other motions were considered in those studies. And so that gives you a sense of both repeatability, but also the differences between them. If we consider our typical low plasticity silts, where your B parameters may be about 0.1, for a magnitude 6.5, maybe something just a little bit less strong than in a Nisqually 2001 earthquake, we're expecting about 75 cycles on average. If we look at a magnitude 7.5, that ups to about 80. And for a magnitude 9 or so, we're expecting about 100 cycles of loading for typical subduction zone motions of that magnitude. Again, these are averages. The range is rather large. And again, we could expect even greater number of cycles. So since we're expecting so many cycles for these materials, I believe it's fairly important to establish the ultimate hysteretic behavior for these soils. So we can relate the number of equivalent cycles for any kind of ground motion to magnitude scaling factors for use with the simplified method. Since plasticity controls the cyclic resistance and the curvature of the CRN curve, it also controls magnitude scaling. And so we use this relationship developed by Ross and Ed over at UC Davis to relate a magnitude 7.5 and the number of cycles associated with that moment magnitude and exponent B to the number of cycles for any other ground motion from a different magnitude earthquake. Naturally, our interface motions and earthquakes are longer with larger numbers of cycles, and so we expect our magnitude scaling factors to be quite different from those of crustal earthquakes. However, for high plasticity silts where there's very little curvature, we're expecting a magnitude scaling factor of 1.0 for all moment magnitude earthquakes. As the PI reduces and we become a low plasticity silt to no plastic, there's really very little change from the prior reported magnitude scaling factors. But as the curvature and cyclic resistance with the number of cycles increases, now we're thinking about clean sands, we begin to see significant differences against the previously reported magnitude scaling factors. And so they're smaller than a 7.5 crustal earthquake for low magnitude earthquakes, and the magnitude scaling factors are likewise a little bit larger, also less than 1 for large magnitude earthquakes based on our analysis. And so we've proposed a regression model just using moment magnitude for magnitude scaling factors, but likewise we expect that other factors control magnitude scaling. So with loading addressed in subduction zone earthquakes, we're going to circle back now to, with the time we have, to resistance and how we might estimate the strength of these materials. But it has been a challenge for those practitioners who work up here in the Pacific Northwest. So to give a sense or relate what kind of challenge we face, we've taken our laboratory-based cyclic resistances for magnitude 7.5 earthquakes, for at least crustal earthquakes, where we might expect 15 cycles of loading if the material is sand-like and can be assessed in terms of cyclic resistance using typical CPT-based liquefaction triggering curves. And we've looked at 30 cycles for those soils which have plasticity and their strength can be assessed using Shanset-based methods. For our samples, which each of these dots represent, and note that the filled markers are colored by different bins of PI, we have applied, especially for the plastic materials, the measured OCR in the laboratory, and we've married them to typical Shanset parameters for these silt materials. With regard to the CPT-based assessments of cyclic resistance, we've corrected for the in-situ vertical effective stresses and the fines content so that the cyclic resistances are comparable on a 1-to-1. And we can see that the cone tip resistance, again, is the geometric average over the height of the sample from which the specimen was derived, and it ranges narrowly between about 0.2 and 10. So for our higher plasticity silts in the laboratory, if we make a Shanset-based estimate of cyclic resistance, we do a great job. It works really well with error of about 5%, which is almost too good to be true. But this gives us real confidence that for high plasticity silts, that we can use this kind of approach to make assessments of cyclic softening. If we look at the lower PI silts, we see that there are a couple of specimens that are well predicted by the Shanset approach, but many specimens are poorly predicted by the Shanset-based estimate of cyclic resistance at 30 cycles. And then when we look at materials that might be classified as sand-like under the cyclic strength evaluation criteria, we can see that our cyclic strengths are quite a bit larger than about 50% relative to those CPT-based cyclic resistances. So it sure seems like lab testing is critical. We want to promote that. But in the meantime, before we can identify scope and budget to do lab tests, we'd really like to make an a priori estimate of the cyclic strengths of these materials. So we go back to the statistical analysis techniques used earlier for exponent B, and we perform stage regression analysis. In the first stage, we want to explore basic trends and functional forms that could be used to estimate cyclic resistance. And again, we are only considering those intact specimens that are sheared under their in-situ stress conditions, except in a couple of cases where we produce artificially normally consolidated states. Then we subdivided the data collected at a given shear strain amplitude into 2 groups. And in separating the data, we were trying to produce data sets that had similar ranges in stress history, or OCR, plasticity, and vertical effective stress, so that we didn't impose some kind of bias into the assessments. And so we reserved about 3/4 of the data at a given shear strain amplitude for training, and then we tested against an independent set of data that represented about 1/4 of the total amount of data. So for 3% shear strain, we've got 83 specimens to train on and 33 with which to test on. Once the trends were evaluated and the suitability of a given functional form of statistical model was confirmed, we then combined the data back, and for a range in strains from 1 to 10%, we would train the final set of model coefficients. So I'd like to give you an example of one of our statistical models at a shear strain amplitude of 3%. Again, on the left-hand side, we've got our training data and a comparison of the model estimated cyclic resistance to that which was measured. And then we've got on the right-hand side the assessment of our testing data. The functional form that we ended on is Shansep inspired. You might be able to detect that in the terms that we have here. But in order to capture non-plastic specimens, we add this PI +1 term to account for the effects of plasticity. The last thing to point out is rather than use the actual B, we're using our previously developed statistical model for exponent B so that we have a truly independent assessment of cyclic resistance. So for this particular model, we can see various goodness of fit measures. Lambda bar is the ratio of point bias, which is the ratio of measured cyclic resistance to estimated cyclic resistance. And the coefficient of variation is just the standard deviation in point bias divided by the mean. So based on our training data set, we have about 17% variability in a relatively unbiased model. Comparing to the testing data, I think this is kind of fortuitous, but we see that we slightly underpredict the cyclic resistance, but the uncertainty happened to go down. But most importantly, all of the coefficients that go into the model to provide these estimates of cyclic resistance are statistically significant. And finding this to be an acceptable model, we developed the final coefficients to have relatively unbiased estimates of cyclic strength with relatively low uncertainty at 16%. So we went and used that kind of formulation for strains ranging from 1 to 10%. The figure on the right gives you a sense just quickly of how the data falls. Clearly, the amount of data decreases sharply after a shear strain amplitude of 3.75%, dropping from 121 specimens down to 48. And the reason for that is many of our tests were conducted with specific termination criteria that was needed in order to identify appropriate post-cyclic performance for a given application. So rather than talk about all these graphs, let's just focus on a few strain magnitudes. So as the cyclic shear strain amplitude increases, the accuracy of this model begins to increase, but we should just be aware that the data representation is continuously changing as we eliminate specimens that were not cyclically sheared to larger strains. And so in our report, we identify those specific limitations where we might need to be careful in making assessments of cyclic resistance and not extending the model far out into the unknown. Particularly large PI specimens were scarce at large strains as well as non-plastic specimens. It should be pointed out that this model is intended to provide the cyclic resistance at a 0.1 hertz, and so there are some frequency corrections that are going to be necessary to use these models. But I just want to talk about a couple of typical trends in cyclic resistance, starting out at a cyclic failure criterion of 3%. I've got over-consolidation ratios of 1.5 and 3, where 3.0 is represented in the dashed lines. Blue curves represent non-plastic specimens, red PI of 10, and black PI of 30. So we can see what the effect of OCR is. It increases, or cyclic resistance increases 33% as you go from a specimen with an OCR of 1.5 to 3 at 30 cycles of loading. If we go from a low plasticity or non-plastic material at 30 cycles, we have an increase to a PI of 10 material of about 32% at 30 cycles, but every additional increase in plasticity produces smaller returns on the cyclic resistance. So these kinds of models could be used as a check on your cyclic laboratory test data. It might be an indication if there's a big deviation in what we have here, that there could be sample disturbance, and there are other variety of uses for these kinds of models. By calibrating the model over a range of cyclic shear strain failure criteria, we can get a sense of how cyclic resistance varies with shear strain amplitude. There's a potential application here for performance-based design. So in general, we capture what we observe in our laboratory test data pretty well. I should point out that we have some unexpected behavior after shear strains of about 3%, and that's because of the reduction of non-plastic specimens in our database as our shear strains increase. So we really don't expect a drop in cyclic resistance as the shear strains increase. None of our specimens displayed cyclic shear softening in testing. However, I think that this is purely an artifact of database representation, and I would expect that the cyclic resistance could be very flat and basically insensitive to greater amounts of shear strain under stress-controlled conditions for these non-plastic specimens. But this kind of model can then be used as a check on your shear strain amplitudes developed from site response analyses. It can be used as a check or as a means to calibrate constitutive models when cyclic testing data is not available. And we can also integrate this with the simplified method for assessments of cyclic failure. So putting it all together, for the strains of 1 to 10%, we've stitched together each of the fitted coefficients and exponents as shown by these fairly hairy equations here. I expect you'll come back to the video to grab them, or better yet, do read the report where we talk about the limitations of these models. But it does give you a sense or a means with which to estimate cyclic resistance as a function of the number of cycles of loading, the plasticity index, the overconsolidation ratio, and the shear strain amplitude. I'd like to point out we developed a similar model for the cyclic strength ratio. Probably not as good as this particular model, but you can also use estimates or measurements of monotonic undrained strength to convert our CRR model to the cyclic strength ratio if you prefer to use that particular type of parameter. As I mentioned earlier, we need to make some strength corrections. Cyclic DSS data that we've developed represent uniaxial loading. We used a frequency of 0.1 hertz. Our apparatus is happiest at that frequency. So we need to account for the strain rate effect. And the literature has shown that soil strength varies by approximately 9% per log cycle of loading rate. Since many of our earthquake ground motions have a predominant frequency of about 1 hertz, although it can vary significantly, we can apply a correction of 9% to the CRR computed using our models. Naturally, you can select whatever frequency or strain rate that you like. Also, our silts in their home deposits will experience multi-directional loading, which is what earthquakes produce. There have been some recommendations to reduce the cyclic resistance in plastic materials by about 4% to account for multi-directional loading. Based on some controlled blasting studies at the Port of Portland, we observed reductions in cyclic resistance of 0 to about 7% relative to uniaxial loading. This seems pretty much in line with the previous recommendations. So sticking with the middle there, we'll multiply the uniaxial CRR by 0.96. And so we can make a conversion to cyclic resistance at 1 hertz for multi-directional loading at what turns out to be about 5%. But naturally, if the frequency content that you're interested in is different, this number would change accordingly. Once we've got an estimate of cyclic resistance, we can make an estimate of cyclic loading or seismic loading using the simplified method. Here we can best use our laboratory data directly to estimate factors of safety against cyclic failure, or we can use an estimate of cyclic resistance, maybe at the 30% level of design in order to or perhaps justify a laboratory test program. But we can now generate strain-dependent factors of safety against cyclic failure anywhere for strains between 1 and 10%. Should point out that there's no reason to use a magnitude scaling factor if you select a cyclic resistance that's consistent with the magnitude and the type of fault source, which drives the number of equivalent cycles to be used in selecting the cyclic resistance. So with that, I think I've approached about 50 minutes with our slightly delayed start. I'll just like to make some concluding remarks. Number one, we feel like material characteristics could be used to estimate liquefaction susceptibility when we're focusing on hysteretic behavior. But best practice is to test your materials. And if you do, take some of those specimens to large strains, because the ultimate hysteretic behavior will reveal whether the material will ultimately liquefy or if it will soften cyclically. Naturally, if we're going to use the various available criteria, let's just make sure that we take care when applying it. And in part of a typical workflow, let's state what our definition of liquefaction is when using various criteria. In terms of loading, subduction zone earthquakes will produce larger number of cycles of loading based on their duration relative to crustal motion. So we might consider using the appropriate number of cycles or scaling factors. And by proposing this model for exponent B, it gives a sense of how to estimate not just the mean or expected number of equivalent cycles, but also its uncertainty, which is remarkable. And we're taking efforts to try to reduce that uncertainty. Back to resistance, we can use these strain-dependent cyclic strengths and make estimates thereof using the proposed models. It can be used to make initial checks, perhaps justify a lab test program, or evaluate the results of some nonlinear numerical analyses you might be conducting. And a concluding thought, based on the results of our in-situ dynamic test, that's really helped us shape our understanding between the similarities and differences of seismic and cyclic responses, but I guess there's just not enough time, so more on this later. And with that, Tim, I'm going to turn it back over to you and just return back to the acknowledgement slide for acknowledging those sponsors and colleagues that made this work possible.
Well, thank you very much, Armin. What a great talk. And we've got several questions lined up, and I think I'll start off with one. Did you perform any post-cyclic strength tests?
Oh, we sure did there. Am I still sharing? I'm not sharing here, but certainly I can talk a little bit about that, and perhaps might be useful to bring up a particular slide. We performed a suite of post-cyclic tests, and let's see how I can share my screen again. There you are. And so I can present a little bit on that for some plastic materials. And we've organized our sites by letter, but this is one of our sites at the Port of Portland. And just presenting some typical results of post-cyclic monotonic strength, where we subject a specimen to particular shear strain amplitude associated with a given maximum excess pore pressure. These are shown here on by the coordinates of strain and maximum pore pressure. And clearly there's a relationship between destruction of the soil fabric, which is kind of directly driven by the shear strain amplitude, and the amount of strain it takes to mobilize any amount of significant strength. So here's just some example results, some thoughts here. We should be thinking about allowable post-seismic displacements. Maybe 15% shear strain is a bit large for stability of structures. But kind of getting back to that question, for this particular site with PI of about 21 to 29 and OCR of 2, we do see stronger post-cyclic strengths than reconstituted, normally constituted specimens. And so that gives a sense of some of the post-cyclic work that we've done here at OSU.
Wow, thank you. And we have one here from Alfonso Serna Diaz. Did you establish critical state lines for the silts tested?
Yeah, that's a great question. Most of our specimens are cyclic, direct simple shear specimens, in part because we're interested in the cyclic behavior for vertically propagating horizontally polarized shear waves, but also you don't need a whole lot of specimen in order to run a lot of tests. So when we wish to develop critical state lines, we'd like to use drained triaxial tests as the primary basis. And we thought that we couldn't afford to use so much specimen or sample for those kinds of tests. So for the majority of our work, we have not determined critical state lines, but clearly that's a linkage that we need to draw in future work.
And he's got some follow-up questions on this. Any insight in the shear compressibility state on the behavior, and then how do you assure undrained response in the T-Rex? Thank you.
I don't quite understand the first part, but I'm happy to speak about T-Rex, and that's that work is described in a journal paper at JGE that was released earlier this year, Jana et al. But we applied 40 cycles of loading at 10 hertz. And during that time, our pore pressure transducers did not observe any partial drainage during shaking. That being said, when we loaded the array with significantly greater amplitudes with controlled blasting, we did indeed see partial drainage throughout the loading time history. And that clearly affected the shear stiffness in terms of maintaining shear stiffness relative to a purely undrained state. And so anytime we develop a 3D pore pressure field or loading environment, we're going to generate, like associated with controlled blasting, and in some cases T-Rex, you're going to develop hydraulic gradients that could lead to partial drainage. So that is one of the effects of not being able to shake the whole world in a one-dimensional state like we might expect with, at the best sense, with earthquakes.
Thank you. This one is from Jimmy Storm. Have you considered a different naming than clay-like or sand-like? It's a very binary perspective, and I already see Plaxis users wondering if they should use undrained A, B, or drained.
Right, that's a neat question. And I really recommend going over to the Peer Center website and downloading the workshop report. And I do understand the concern there. It boils down to succinctly identifying whether transient liquefaction can or cannot occur. We do tend to operate in this binary framework. The entire geotechnical profession has been built upon this from the very beginning, and we should get away from it. If you noticed, I did have a suggested range of hysteretic metrics for intermediate materials, and clearly behavior varies or evolves throughout loading. And so we could have different usages of these terms for the same material under different loading conditions. So it's definitely a gray zone. I'm sensitive to that question. I appreciate that question. I don't have an answer for Jim at this time.
Excellent, thank you. This one's from Jared Martinez. We are talking sand chip and lab-based OCR. What consolidation testing method, constant strain, was performed to test OCR, and was disturbance calculated for these samples?
Yeah, great question. We like to use constant rate of strain at a relatively low strain rate. It allows us to improve our estimates of the pre-consolidation stress. That's our primary motivating factor for performing those assessments. And Jason DeYoung over at UC Davis has developed another sample quality assessment approach to complement that by Linney and by Terzaghi. And we like that approach, which uses ratios of the initial recompression index to other recompression or compression indices. And basically, we tend to see either high quality or good quality samples based on that assessment, or when they're moderate, they're very close based on the selected range of recompression ratios to the good quality. So we have pretty good sample quality based on the techniques that we use, and we can certainly recommend our sampling of procedures and handling procedures for our materials. Summary of our sample quality is in one of our 2023 papers on this lab work.
Thank you. I see, I guess we've stopped posting the questions. I have one question of you, Armin. How can you estimate the loading to be used with the simplified method for magnitude 9 earthquakes?
Oh, Tim, you had to leave off on a bad one, huh? On a strong question there. Well, if you read Ross Boulanger's and Ed Idris's work, they do advise caution on calculations of loading, not just for magnitude earthquakes of that size. We've got one major event, right, Tohoku, that's 9.0 or greater, but also the shear stress reduction factor also has a depth limitation that they clearly state. And here in the Pacific Northwest, we have deep deposits that could be subjected to magnitude 9 earthquakes. So at this point, I think that an appropriate approach, given that a user has significant experience and skill, and thus a team of engineers of experts could conduct site response analyses. Maybe starting with equivalent linear, moving to total stress nonlinear site response analyses, and calculate what the peak shear stress amplitude would be for a given motion and run a lot of motions. And once you take a look at your site response analyses, assume they're run appropriately and correctly, you might factor that peak shear stress by 65%. Maybe take the average and evaluate the uncertainty for the motions that you've run to bound what kinds of cyclic shear stresses you could expect, and then apply those with your estimates of cyclic resistance to give an acceptable strain magnitude or a selected failure criterion, and use the simplified method in that manner. That might be a real appropriate approach to justify a lab testing program and perhaps more advanced nonlinear dynamic analyses.
Well, thank you. Thank you very much, Professor Stuedlein. This was a great presentation. We appreciate your time and effort you put into this. Behind me, you can see this wonderful certificate we've made up. We're going to be sending that to you in its beautiful little folio. And we appreciate your input and efforts on this. Stay tuned. I guess the next seminar we're going to be having is in June 15th. And I'll leave it to you, Brad.
And I'll tell everybody about that next seminar in just a moment. But first, I have to, why not produce some kind of NFT certificate for Armin there? I mean, it could be a unique thing. These could sell for hundreds of thousands of dollars on the secondary market.
Sign me up.
So we do have the next episode 4 in the seismic series coming up on June 15th. You will want to participate in that one. The link is over in the chat box to the right of where you are watching this. It's on the seismic stability of PG&E's Diablo Canyon nuclear power plant. It's with Jeff Bachhuber, and that again will be on June 15th. Our next live stream overall for GI is June 6th, and that'll be Tim Stark of the University of Illinois doing one of his live streamed Cross USA lectures. We'll have 3 of those this summer, one in June, one in July, and one in early September. So again, thanks for sticking with us till the end. I hope you liked it. You probably did because you are here at the end. Click like, subscribe, get notifications. Of course, we will let you know lovingly with all kinds of love and care in our hearts whenever we post something to the YouTube channel. So Armin, thanks for a great lecture today. Tim, thanks for another great episode and for running the show. We really appreciate it. For all of our viewers, we will see you next time.
Thank you, everybody.
Thank you.